Universal gravitation is a calculation we'll be making on the gravity calculations. And I'm going to do an example for you here that is just like the ones you're doing, except for the last one that's a challenge. But I'm going to do it with two of the objects that I did not give you on the sheet. So remember that between any two objects, even these actual little spheres, these little balls, there is gravity between them. Any two masses have gravity. Of course, the gravity between these would be very, very tiny, difficult to even measure, okay? But the gravity between larger objects is more noticeable. So any two masses, anytime you have two masses, there's gravity between them. It's the force felt by either one. Now it's important to realize it's the same force felt by one of them as felt by the other is dependent on big G, the universal gravitational constant, which has these values over here, this value. And one of the masses multiplied by the other mass, multiplied together, and then divided by the distance between them, but squared. Not just the distance between them, but the distance squared. So if these were, let's say, 8 centimeters apart, the center of mass, if it was 8 centimeters apart, well, you would square that. That would be 64 centimeters squared. Of course, we wouldn't use centimeters here, but the distance between them is of major importance. Now, let me point out that Einstein actually showed us that this, which is from Isaac Newton, Newtonian physics, isn't entirely correct. There are some relativistic effects that this doesn't account for, but even Einstein used the gravitational constant, the universal gravitational constant, in his equations, so it is a really good number to use. One way that Einstein pictures space, imagine like this is a aluminum foil on top of a bowl. It's nice and smooth. If you take away one of the dimensions of space, you could represent it two-dimensionally by a flat surface. And then if you put a little object on it, it makes a dent. It makes a dent in the universe. Other objects that are nearby are pulled toward it. That's really what is causing gravity. That's what Einstein showed us. It's the warping of space around masses, which causes them to move together. That was a good example. And let me see if, I don't know if the aluminum foil will hold up this mass. Oh yeah, it will. Okay, so, and then if I put this one sideways, it'll roll towards it. So that's the same kind of concept. It makes a dent in the universe. There we go. Dent in the universe. Boom. There we go. Okay, so what I'm going to do is I'm going to calculate, use the equation above for universal gravitation to calculate the gravitational force acting between the Earth and the Sun. So in order to do that, we need the mass of the Earth, and we need the mass of the Sun, and we need the distance between them. Now, usually we talk about the distance between the center of each object, at least the center of mass, which is usually the center of the object. Okay? So that's what we're using here. Let me point out that G is a constant. Constants are your friends because they're very reliable. You always know what a constant is going to be. That's what G is, always. And why is it called the universal gravitational constant? Because you can use it on any two objects anywhere. Well, we are in the universe right now, by the way. The Earth is just as much a part of the universe as M87, okay, or the Andromeda Galaxy. This is the universe right here, so of course we can use it here. But there's also another G, a lowercase g, which is the gravitational acceleration on Earth that we'll honestly be using much more than this. So this is just getting quantitative, using numbers in scientific notation, multiplying, okay, number crunching, dealing with units. There's a lot of activities that depend on this. This is really good exercise for us. Okay, so if I'm going to figure out the force, and by the way, I do want to mention again that the force on each object is the same. So the force that you calculate is going to be the force felt, the force acting on one of the objects. But it would be the same force acting on the other object. So we're just going to calculate F, okay, as the force acting on each object. Okay? So, first of all, what do we need to do? Well, let's write our equation and put the numbers in the right place. We've got f, which is what we're solving for, is equal to g, well there's g, 6.674, and we've got g to several digits after the decimal. Usually we would round off to here, but for g it's good to know a more precise number, times 10 to the negative 11. Is that a big number? Is that a big number, negative 11? No, that's a small number. And then the units of g are meters cubed per kilogram seconds squared. Now this happens, and I'll put a dot between those to separate. Now this happens a lot with units of constants. The units of constants are usually really weird. That doesn't really mean anything. That on its own doesn't mean anything. But once we multiply it by these, what we come out with will mean something. And by the way, if you look at the units of your constant, okay, m is meter, that means that we need to use meters for our other numbers. Which of these would be in meters? Not that, because that's mass. Mass would be in a different... Oh, r, distance. So that's why, of course, we have the distance here in meters, because the units of the constant are in meters. Okay? And then what's the unit of mass got to be? Look at this. That's got to be kilograms. So we can't just put in grams. This won't work if you just put in grams, or if you put, it would not work if you put in any other unit of mass. Let's not even talk about those, or units of weight that people get confused with them. Okay, so that's my g. Now I've got my little, let me just draw the fraction bar. And of course, if numbers are next to each other, they're multiplied. Okay, and then if it's on the bottom of a fraction, it's divided. We could have just put the g in the numerator, but this is normally where the g is put on its own. Okay, if you want to see g a little better, I'll put little parentheses around it so you can see that that's separate. That's just one number. Okay, so now we've got the mass of the Earth. We need the mass of the Earth. Oh, here it is. The mass of the Earth, which is 5.97 times 10 to the 24th kilograms. Now, you might not have known that was the mass of the Earth, but it is. And then that gets multiplied by the mass of the other object. Oh, the sun. The mass of the sun, well, it better be a lot bigger than the Earth. Let's see. 1.99 times 10 to the 30th kilograms. Okay, that's a lot bigger. 24th here and 30th there. Let me just darken this a little bit so you can definitely see it. That's actually a huge difference. Think about it. It's how many more times you have to multiply by 10. 6 more times multiplied by 10. We're talking about 1,000,000 times different, almost, because these numbers are not the same. But much, much different. Okay, and let me extend my little fraction bar over here. And then in the denominator, what do we got? Oh yeah, we need r squared. So again, because of the units, the distance between them, and why is it called r? The reason it's called r is radius, right? But think about it. If we're talking about two objects orbiting each other, like let's say this one's going around that one, well, it's the radius of that circle, sort of, right? So that's why they decided to call it r instead of just d. Usually these objects would, well, we won't get into binary systems, but if you think of one object is going around the other in a circle, pretty close to a circle, well then it's r between them. So r is the distance between them, by the way. It's exactly this. So we've got 1.50 times 10 to the 11th meters squared. The whole thing is squared. So now we're going to see some of the advantages of using numbers in scientific notation. Multiplying and dividing them is very, very easy. I prefer to use a very simple calculator, not even a scientific calculator, because I don't think you need it, and I think it helps you keep track of what you're actually doing. Okay? So let's see, what order should we do this? I think the first thing I want to do is crunch these numbers together, multiply those together, and I'll square this. So I'm going to rewrite this equation with g still there. I'm going to keep the g there, and I'm going to multiply the numerator together, and I'm going to square the denominator and have that all ready. So let me rewrite the portions that will be the same. We've still got f equals, and we've got g. I'm going to write it a little bit smaller now. 674 times 10 to the negative 11 meters cubed per kilogram second squared. Okay. Now, to get this numerator to work out, first thing I want to do is I'm going to multiply 5.97 times 1.99. I'm multiplying these first portions here. Remember, first thing you want to do, multiply those portions together. All right? And what I get from that is I get 11. I get 11.88, and I think I'm just going to round it off there. Okay. Then I want to deal with the exponents. Okay. And the exponents are 24 and 30. We're multiplying. So what do we do? What do we do with those exponents when we're multiplying again? What do? You add them, correct? So we add them together, and we get 54, right? So we get 10 to the 54th power, which is a huge number. And then, oh, it's kilograms times kilograms. What would that give me? This is a concept that is hard to even think about. Kilograms squared. You know, what would a kilogram be if you squared it? How would you square a mass? That's a weird concept. But don't worry, that's not going to be an issue in the end when we get our final answer. Okay? So that's what happens to our numerator. Oh, but wait, of course we want to move the decimal over to get it in proper scientific notation. So really what this would be, if I were to write it correctly here, I would move the decimal over 1, and then it would be 1 point, let me see, where can I write this? I'll write it up here. It would be 1 point, 1, and then if I were to round to that position, this 8 would round up to a 9, 1.19 times 10 to the, I'm going that way, so what would that change the exponent to? 55th kilogram squared. So the reason I'm writing it up there instead of here is because I don't have enough room to write this too many more times. Okay, I might have to add paper on the bottom if necessary. Okay, so that's my numerator, and this would be proper scientific notation, but for now I'm just going to leave that. Let's deal with the denominator now. The denominator, well, it's this number squared. So it's 1.50 times 1.50 equals, and that gives me 2.25. And then if I multiply 10 to the 11th times 10 to the 11th, okay? So like, again, we dealt with the first portion, now we're dealing with the exponents. Well, it would be like adding 11 plus 11. That would give me 22 to the 22nd power. Now notice, and what would my unit be? Meters times meters, meters squared. So remember, we squared this number. So I could have just written it twice. I could have written it here and here, and we did the same thing we did in the top, but we did it with the same number for both of them. So it was 1.5 here and 1.5 here. 10 to the 11th here, 10 to the 11th there. So we get this number. This one, we don't have to move the decimal. This is already proper scientific notation form. Okay, so now when we deal with these in the next one, I'm going to, we could do this either way. We could either divide here and then multiply together. I think that is what I'm going to do. Or we could multiply these two together and then divide. The order of operations for that don't really change the answer. But just to keep things the way that I'm writing them, I'm actually going to keep, once again, I'm going to keep big G over here on its own, 6.674 times 10 to the negative 11 meters cubed per kilogram seconds squared. That's one number. Now we're going to have, after we divide these, we'll have the quotient that'll go here. Okay, so whatever we get from this is going to go right here. Now, you know what? Even though this is not proper scientific notation, actually it might be easier to use that number instead of this one. And you'll see why. Because then I might not have to move the decimal here. So it is sometimes okay to leave numbers in improper scientific notation when you're actually working. Just never give that as your answer. Never ever put this, like something like that, as your final answer with 2 digits in front of the decimal. So what I'm going to do is I'm going to ignore the proper one. I'm just going to use that and divide it by this. So watch what happens. When you divide, now remember, it's just like multiplying, except you're dividing. Okay, you take the first portion divided by the first portion. The numerator divided by the denominator, of course. Even though, amazingly, some people forget the order to do that. 11.88 divided by 2.25 gives me, and what color am I going to write this in? I guess I'll just make it black. Okay, 5.28. So notice, because I divided that one, I do not need to move my decimal now, so it left me off with a good number here. Okay, so if I had done that one, I would have had to move the decimal after this. So in a way, I didn't move the decimal here, and it saves me from moving the decimal here. So I'm getting a reward for my bad habit. It's kind of funny. You shouldn't be rewarded for bad habits, right? But here I was. Okay, and then what happens to the exponents when you divide? Well, of course, it's like subtraction. So it's the one on top divided by the one on the one on the bottom, so it's like subtracting them. So it's 54 minus 22 equals, okay, so I just subtracted this number minus that number, and I get 32. So what happens with my units? Well, I had kilograms squared, I had kilograms squared on top, and I divided by meters squared, so now it's per meters squared. So now really, all I have to do is essentially one more step. I have to multiply all of this, which remember, this number came out of all three of these. I've just crunched them all together. Now if I multiply by this, boom, I should get my force. Okay, I think I'm going to have to move the decimal, so I'm going to try to leave it so I have room underneath to write one more line. So I'm going to write this one. You may notice I'm writing them a little bit thinner as we go along, just to leave room. I should have left more room for myself. Okay. So the first thing we're going to do is we're multiplying again. So we're taking the first portions and multiply together. And by the way, if you ever get confused, like, why am I not using first, outer, inner, last? Why am I not using FOIL here? It's because this is really just one number, and this is really just one number. It's not actually two numbers. It's just one number in another form. Scientific notation is a way of compressing a number, but that's still just one value. So if I take my 6.674 times 5.28, what I get is 35.24. I'm going to round things to the hundredths place. I'm rounding 2 digits after the decimal. That's what I generally recommend people do for the most part. Even though this one had 3, notice how everything else I've been rounding to 2 digits after the decimal. That's the best way, I think, to remember what to do. Okay, and then what happens to my exponent? Now this is a little tricky because this number is a negative exponent, meaning that it's a small number. Not that it's negative, that it's a small number. We're multiplying, so we're adding, right? So we're adding negative 11. It's sort of like this. It's negative 11 plus 32 equals, well, I could rearrange that. 32 minus 11 would give me the same answer, right? So it's a negative number plus a positive number, so you can always shift them around the order that you do it. So I'm going to do 32 minus 11, and I get 21, and that is my new exponent, 21. And then, oh, what happens to my units here? This is the interesting thing. Okay, so I've got, let's deal with meters first. We've got meters cubed on top and meters squared on the bottom. So you're going to be left with only 1 meter on the top. 2 of these are going to cancel out. So these are going to cancel out, and we're going to lose that exponent, actually. We're just going to have meters. And what about the kilograms? Well, we've got kilograms squared on top and kilograms on the bottom. So what are we going to be left with? The kilograms on the bottom are going to cancel out. We're going to have 1 kilogram on the top. So because of the way we normally write this, I'm going to actually put that before the meter, and I'll put a dot in between them, okay? And what about seconds? Well, this one doesn't have any seconds. Oh yeah, and so let me cross out that 2 then. This one doesn't have any seconds, and this one has per second squared. So the per second squared is still going to be down there. So kilogram meters per second squared, Okay, you might not have seen that one before, but that one actually comes up quite a bit as a unit of force. Okay, so kilograms meters per second squared, so the units are good. And wait a second. And we won't talk about converting these into another unit. We'll just leave them like this for now. Okay, so force, there's one problem here. We don't have it in the proper scientific form. So we're going to write force equals, we're going to move the decimal over 1, so it's going to be 3.5, and then we're just going to keep the 2 now, because we're only keeping 2 digits. We're going to drop that 4. 2 digits after where the decimal happens to be, times 10. What does that do to my exponent if I move that way? It was 21 there. What would it be there? 22 to the 22nd, and kilogram meters per second squared. So we'll talk about, this can actually be turned into another unit, but you know what, for now, I think we're just going to leave it like that. And you can make sure that your answer has a unit, that it's in proper scientific notation, and that's really all we're going for right now. It's an exercise at using what appears to be a pretty challenging equation, using a pretty crazy looking constant, and calculating the force attracting the Earth to the Sun. So this is the force acting on the Earth. This is also the force acting on the Sun. The Earth is pulling on the Sun, by the way. It's not just a one-way, it's not a one-way street. Okay, any two objects, they have gravity between them, they pull on each other equally. So because of the way I phrased the question, you only have to give one answer. But just remember, that's the gravity pulling on the Earth from the Sun, and that's the same gravity pulling on the Sun from the Earth. They pull back on each other, back and forth. Okay, so all your other calculations are just like this. The only other one, the last one, which is a challenge, you have to convert. I'm giving it to you in weird units. So you have to convert to make sure you're in the right units. Now remember that pounds are not really mass, but if you're here on Earth and you measure your pounds, if you divide it by 2.2, you get your kilograms. Now that only works if you know what the gravity is. Later on, you're going to see why when we use little g. But let's say, for example, if I'm like 220 pounds, or at least I was maybe a little more now. It's 1 kilogram per 2.2 pounds. So actually, I think I spoke wrong. You divide by 2.2, divided by 2.2, you get 100 kilograms. Now, technically, that doesn't fully work because kilograms is a mass and pounds is actually a weight. So they're different things. But if you assume that you're under 1g, regular Earth gravity, then you can do this conversion. So you might have to do that if you do the challenge, which is optional, the last one. You convert into kilograms, of course. And then, of course, don't forget to turn it into meters. You can look that one up. Okay? So, good luck on the gravity calculations. They're all just like this. The only thing that this will be the same. This will be the same. This will be the same. These will be different masses. Okay? And the distances will be different. Actually, one of your examples does have the Earth, and a different example has the Sun. Okay? But it'll never be these two together. I did not give you this actual one. So that's how you do gravitational calculations. Good luck.